In this video, we're going to have a look at how we can think about equilibrium in a slightly more mathematical way in terms of the position of equilibrium and looking at something called the equilibrium constant. So the equilibrium constant is Kc is in terms of concentrations. Now there will be further equilibrium constants you will look at in the course, and the subscript is very important because this little c represents the concentrations. So when we've got an equation like we have here, where A moles of A react with B moles of B, what that means is that there may be maybe two A's, it'd be A plus A and then B plus B. We could have multiple A's and multiple B's and making C and D. That we can express the value of the position of equilibrium in terms of the concentrations by putting the products of our reaction on the top line of a fraction and the reactants on the bottom line. So we can say how much products are there comparative to reactants, and we're looking at concentrations, so we're using these square brackets to represent concentrations. Now things that were added in our balanced chemical equation are now going to be multiplied. So if we have C moles of C, that would mean we would repeat C however many times. So say that was a 2, it would be a C add a C in our chemical equation. It now becomes C times C, and so we can represent that as a squared. So the numbers that were the moles now become the powers, and all these terms are multiplied together. So the important things are it's the products on the top and the reactants on the bottom. Square brackets are essential to represent concentration, and then the powers that you use for each thing relate to the number of moles of each thing that there are. Now there's some significance to this number then, isn't there? Because if this Kc is an expression where we've put concentration of products on the top and concentration of reactants on the bottom, then the size of that number will give us an indication of where that position of equilibrium lies. So if that number is significantly smaller than the number 1, then we know that our fraction is a bottom heavy fraction. And if our fraction is a bottom heavy fraction, what we can say is that the concentration of the reactants is higher than the concentration of the products, and that means that our equilibrium lies to the left towards the reactants. And then if our number is much bigger than 1, we know we've got a top heavy fraction and the concentration of our products is much greater than the concentration of our reactants, and we'd say our equilibrium lies towards the product side, which is towards the right. So a really big number means lots of products, an equilibrium that lies to the right, and a really small number means that the concentration of reactants is higher and our equilibrium lies to the left. Now, given that each equilibrium that we come across has a unique chemical equation, we can see that it'll have a unique Kc expression, and as such the units are going to vary. It's always going to be in terms of concentrations, which are moles per decimeter cubed, but the numbers of each of those things will vary, and therefore our units for Kc will vary. This is not a universal constant. It's a constant for a particular reaction, so each reaction has its own units at a particular temperature. So we need to be careful. It's not the same as a fundamental physics constant that would have constant units. So let's just have a go at working out the units for a couple. Let's have a look at this reaction to start off with, where we've got PCl3 reacting with chlorine to form PCl5. So the first thing we need to have a go at is, can we write a Kc expression? So a Kc expression goes Kc equals, we're going to put the products on the top line. We just got PCl5, and remember it's concentration of the product. We've only got one of those over concentration of the reactants, and we've written a Kc expression. Then we can have a look at the units. Now I don't like to put all the units in straight away. What I like to think is that I've got a concentration term on the top, and then I've got concentration terms twice on the bottom multiplied. So I've got concentration to the power 1 over concentration to the power 2. Now using the power rules, if you divide the same base with different powers, you're going to do 1 minus 2. If you do that, you get concentration to the minus 1. Now again, I'm going to use some power rules. I know the units of concentration are moles per decimetre cubed, and I need to give that to the power -1. Now when I multiply out this bracket, remember that this is moles to the 1 when you don't put a power next to it. So 1 and -1 multiplied out becomes moles to the -1. And dm -3 and dm and -1 becomes dm +3. So the units for this expression would be mole to the -1 dm cubed. So let's have a go at another one, another expression. So this time we've got something a little bit more complicated. We've got C2H5OH, that's ethanol, reacting with water in an equilibrium with carbon monoxide and hydrogen. So if we were to write a Kc expression for this, again we get the product. Now we've got carbon monoxide, but we've got 2 of those, so it becomes, remember that they're now times by each other rather than added. And then we've got hydrogen 4 times, so we get it to the power 4. And then we're going to divide by ethanol and water, each to the power 1. And then we can have a look at our units. So just in the same way, we've got 2 concentrations and 4 over 1 times 1. So 2 add 4 is 6, 1 add 1 is 2, 6 take away 2 is 4. So we've got the units of concentration all to the power 4. Now if we expand that bracket out, we're going to get moles to the 4, dm to the -12. So as we go on to these next few, we've got 3 examples. What I'd like you to do is just have a go at writing the expressions and coming up with the units. So pause the video now and have a go, and then when you've had a go, come back, unpause the video and see if you've got those correct. So there we go. One to watch there is on that top one. You'll notice that all the units are going to cancel out, and c to the 2 over c to the 2 just becomes the number 1. And if you multiply any value, which you would remember, you would get a value out of this when you put numbers into it, by number 1, it is just that value. There are no units. The units have cancelled out. On this next one, you can see there we've got 2 more concentration terms on the bottom than the top. This becomes moles to the -2, dm to the power 6. And the bottom one, the last example, we've got 3 over 2, 3 terms over 2 terms. So we've got the units of concentration.